All right, so magnetic force F equals Q times V cross B. We'll do a few sample problems with this equation. Remember that what it says is that if you have a magnetic field, you have a magnetic field B that, let's say, points like this, magnetic field B, and then you place a charge Q somewhere in here, and this charge Q moves at speed, velocity V. Then there's going to be a force on it, and you can calculate the magnitude of that force by doing the following: Q, P, E, sine of the angle theta, and the angle theta is the angle between B and B. And you can determine the direction of the force by using the right-hand rule. So the right-hand rule is also something you could use here. Maybe I'll draw the right-hand rule here because this might become handy. So the right hand with the right-hand rule goes like this. You align your hand in such a way that the fingers correspond to the magnetic field B, and then the thumb points in the direction in which charged particle is moving, so that's V, and the force itself would come out of the palm of the hand. So just going to put a little that here to indicate that the force comes out of the palm of the hand. All right, and so now let's try a few sample problems. This one is from page, so I'm going to put here page, this is in a book that we use for algebra-based physics, and this is page 826, number 22. So I may have to modify this a little, we'll see. So there's one thing that I'm going to change about this problem. But anyways, what we have is, let me start with a picture, and if you don't have the book in front of you, you should be able to figure out what's happening in the problem by looking at the setup here. So here's the coordinate system. Now the book calls this the z-axis, so we'll keep that as z. And then this is the x-axis. Now the y-axis, so interestingly enough, the book, we're going to call, this is what I'm going to change. I'm going to say that this is the y-axis. The book has the y-axis point in the opposite direction. It's just, you can do that, but that's a little weird, so I won't do it. And we place a positively charged particle at the origin. So here's a plus. Right, it sits at the origin, so this is Q. Now Q, let me see. Q should be given, it's a proton. Okay, so the charge Q is just a proton. I'm going to put here that Q equals 1.6 times 10 to the minus 19 coulombs. And now let's see. The magnetic field points along the x-axis. So here's the magnetic field. Points like that. The magnetic field. It is half a Tesla. So I'm going to put here that B is 0.5 T. That's the magnitude. And so there are two. Well, anyway, so then the velocity is 1 times 10 to the 7th. So let me state this here: the velocity v. That's 1 times 10 to the 7th meters per second. And then the direction of the velocity vector is like this. Right, now this velocity vector is in the xz plane. All right, so this is in the xz plane, and about it. It's in the xz plane, which means that the velocity vector has some x component, so some vx. It has no y component, and then it has some z component, vz. All right, so this is the picture we have, and the angle itself is actually given to us, the angle between V and B. This is just 45 degrees. I'm gonna put 45 degrees. All right, so this is the problem, and the question is, of course, what is the magnetic force? And we need to figure out both the direction and the magnitude. So find the magnitude of the force and find its direction. So I'm going to state it in the vector form. All right, so let's first figure out the magnitude, because that should be an easy one. Let's do it down here. So then the force would be Q times V times B times the sine of the angle theta. That's 1.6 times 10 to the minus 19th times the speed, which is 1 times 10 to the 7th, times the magnetic field, which is 0.5 Teslas, and then this is times sine of 45. And this is easy to calculate, so let's figure this out. All right, so I got 5, let me put this here. So I got 5.7 times 10 to the minus 13th newtons. All right, so this would be the magnitude of the force. Now, as far as the direction is concerned, you could go two routes. You could either use the vector equation to do this, that is, force equals Q times V cross B. And so if you could just do cross between V and B, then you would have your direction. And it should be easy to do this, since V velocity vector is, well, you could figure out the X and Y and Z component. So you could figure out Vx, Y is 0. You could figure out Vz. That's easy to do. One is cosine, one is sine. This one here would go with the cosine. This one here, the Z component would go with the sine. And then the magnitude, rather the vector for the magnetic field, this would be, well, it's just 1 times 10 to the 7th for the X component. There is no Y component, there is no Z component. Then you do the cross between the two. And you figure out whatever vector you get from the cross is the vector that points in the direction of the force. But why bother? You could fairly easily figure this out using the right-hand rule. So in this specific case, what you would do is you would draw your fingers pointing in the direction of the magnetic field. So let me do that. So these are the fingers here. 1, 2, 3, 4, and then your thumb. Just make it maintain the angle. That's about it. Right. So this is your right hand. And so now what we have is that the velocity points in this direction. This is V. Magnetic field points in direction of the fingers. So this is B. And the force just comes out of the palm of your hand. And so in this specific case, the force itself would go in just the right direction, right? So if this is palm of the right hand. Wait, actually, the force would be so this would be into the page in that case, right? Hold your right hand, magnetic field points to the right, V points where it does. The force is out of the palm of your hand, so you'd have the force. It'd be a little tricky to draw. Maybe what I could do is let me get rid of this dot. Let me see if I can draw it a little farther out. So what I'll do is I'm going to put a dot somewhere out here, and the force here would point like that. This is force where this is at 90 degrees to the palm of the hand. And I put that there so that it'll be less congested. So then in that case, the force may be in white also acting on this would just be in a negative y direction, right? So then the force would point into the page here, but since I drew it in 3D, I'd have to draw this vector of the force like that. But this is simply an extension. So F is an extension of the y axis. It just goes into the page there. It would be negative y. So the direction of the force, I'm going to put here. Direction of the force is negative y. All right. Now this was part A of this specific problem. So I'm going to label this as part A. And I'm going to move on and I'll do part B. Part B is very simple. Part A wasn't very complicated, but but it might be a little tricky to see what's happening. In part B, we have a picture that is very similar, but something changes significantly, and that is we still have the y, we have the y-axis like this, we have the x-axis here, we have the z-axis. The magnetic field still points in the same direction, so the magnetic field points to the right. Here's B, and then we take the charge, positive charge, we place the positive charge right here, and then this positive charge moves with a velocity that is also in the x direction, but it is in the negative x direction, so here's the velocity v. Right, well, let's calculate the magnitude for this thing. So F equals Q times V times B times the sine of the angle theta. And, well, what's the angle theta? What's the angle theta between V and B? Well, it's 180 degrees. And so whatever you have for Q, whatever you have for the actual speed, whatever you have for the strength of the magnetic field, all of this is multiplied by the sine of 180. And the sine of 180 is 0, so you get 0 newtons. And it is true, and this is it. There's, as far as the direction is concerned, there is no direction of the force because there is no force. So part B is done. But let me generalize something out of this. So if you have a magnetic field, points like this. If the charge Q moves in a direction that is either parallel or anti-parallel to the magnetic field, then there will be no force. In this case here, force will be 0. So if V is parallel to B, then force is 0. Okay, we're going to do one more that is kind of like this. It's a different problem on the same page. I'm just going to label it part C, even though there's really no part C in this specific problem on that page, but it's very similar in its format. So let's label this as part C. So suppose that we have the z-axis that points like this, and then we have the x-axis that points like this, and here's the y-axis, points like this. Then you have a magnetic field which points again along the x-axis to the right. This is the magnetic field. Now the charge is placed at the origin, but it's a negative charge, so it's minus. And the velocity of this charge now is in the zy plane. It's also at 45 degrees, so let's see if I can draw this. So this is the velocity vector. But keep in mind that this belongs entirely to this plane here, the zy plane. So here's the velocity vector. I'm going to actually write this here. Velocity is in zy plane. If I were to write out the velocity vector, I would have to write it as 0 for the x component, and then some vy, and then some vz. But there would be no x component of this velocity because this velocity belongs entirely into to the zy plane. All right, now also note that the charge Q is negative. So let's calculate the force and let's figure out its direction. Well, in the first place, we need a couple things more than velocity is not enough to solve this problem. What we need is a charge Q, and in this specific case, it's an electron, so it's 1.6 times 10 to the minus 19th coulombs. There's no need to put negative here. You're interested in the value of the charge, so I'm going to put your absolute value of the charge, and that's just 1.6 times 10 to the minus 19th. And then the speed of this electron is the same as before. It's 1 times 10 to the 7th meters per second, and the magnetic field B is half a Tesla, 0.5 T. So from all of this, it's easy to figure out the force, the magnitude of the force. Q, V, B, sine of the angle theta. So let's plug in the numbers. We'll have 1.6 times 10 to the minus 19th times the speed, which is 1 times 10 to the 7th, times the magnetic field, which is 0.5, times the sine of. All right, now we have to figure out the angle theta. Now remember the angle theta. Angle theta, that's the angle between V and B. So what is the angle between V and B? Well, phi is entirely in the ZY plane, and ZY plane is perpendicular to the magnetic field in this case. So you have 90 degrees, just like you have 90 degrees here. You also have 90 degrees between here. Let me try again. 90 degrees between here and here. That's 90 degrees right there. Right, so theta is 90. And so now I can go back to the equation here, and I can write that this just becomes 1.6 times 10 to the minus 19th times 1 10 to the 7th times 0.5. And then sine of 90 is just 1, and then you get whatever you get out of it. So let's calculate that. So this is 8 times 10 to the minus 13th newtons. Yeah, okay. So that's the magnitude of the force. Note that I did not put negative in front of Q. This is Q. This is a charge of an electron, but I did not put negative in here. There's no need to do that. You're interested in the magnitude of the force, and the magnitude is always positive. So just put the absolute value of the charge here. Okay, we have the magnitude of the force. Let's figure out the direction of the force. All right, so let's redraw this. Here's the coordinate system again. So what I have is y, x, and z. Then I have the magnetic field that points in the positive x direction. So this is a magnetic field B. I have the velocity vector. The velocity vector is entirely in the zy plane. So something like this, where here we have that. This is at 90 degrees. Right, and then here we have this piece where that's also at 90 degrees. There. This velocity v is entirely in the zy plane. Suppose that I redrew. So okay, so I'm going to add something to it. Let me add this. Here's this line, which points in the direction of the x-axis, and then here's this line, which points in the direction of the velocity vector. I want to refer to this plane here, VB plane. So I have 90 degrees here. Try to draw this a little better. 90 degrees here. I have 90 degrees here. Of course, I have 90 degrees here, and I also have 90 degrees here. I'm going to add something to this picture. Maybe that will help understand. So I'm going to add. What I want to do is I want to maintain the parallel. So let's say that I add something to the effect of this. And this forward, farther, but right to this here. All right, and now hopefully you begin to see something what I'm looking for. I don't really know what I'm looking for. Extend this. It's a little iffy there. Again. Goes, and I want to keep this angle. That's actually not too bad. Then what I can do is I can go from this axis, go like this. Just in here, and then I'm going to close this whole story. Right, so I have this 3D shape here. And I'm only interested in a plane that is formed by the velocity and the magnetic field vector. Right. So suppose that I take this plane, the velocity v and a plane formed by the velocity v and b. Suppose I take this side of the shape I just drew, Let me flip it so that what I have is, going to rotate this a little. What I have is a, let's say B points like this, and then B points like this. So here's where I have that plane. If this were the case, and I have 90 degrees here, if this were the case, which way would the force on a charged particle point? Let's consider the negatively charged part. Well, first let's consider positively charged particle here. So let's say that this is a positively charged particle. Which direction would the force point? Well, you could use the right hand, have the fingers of your right hand point in this direction along B. The thumb points in this direction, and then I can easily figure out that the force itself would just point like that. So this would be the force, and then this force would be perpendicular to this, right? 90 degrees right here. Draw this here. And then what I could do is I could take this whole plane here and I could rotate it so that it actually corresponds to the plane of that side of the shape, 3D shape here that I drew. So I take this point and I rotate it like so, and I take this force vector and I rotate it like so. And now this thing would correspond to that side of the 3D shape I drew. And so this kind of gives me an idea of which way the force would point. It would point into the page, but slightly at an angle. However, this is not a positively charged particle, but a negatively charged particle. So let's clear this up. The force would have to point downwards. So let's get rid of all of this, putting that, and now let's put negative here. Force would actually have to point downwards. So the force has to point downwards. This force F. And now let's flip this up. Let's take this point and let's rotate this upwards a little, like this. Then what I would get is that this the force here would point, well, so this is the difficult part. I would have then that the magnetic field B still points this direction. V now points properly somewhere here. And then I have this plane that has been rotated up. And the force F would come out of this point like this, and I would have 90 degrees, that stuff, pointing like this. All right. So that would be the direction that I would need here. If this is a negatively charged particle, then the force would point like this. And I put here F, and it would be perpendicular to that plane. I'll put here that. And this, I think, is probably the best that I can do for you. But this piece here would be easier to show this if I could use a piece of paper and rotate it in front of you, but we have what we have. Okay, this will do for this part.